This review, we're supposed to do Celebration 1 and Celebration 2. You were supposed to come prepared with your questions that you wanted to see done. So, I've got them. I only had one of them as a PDF file, the other one as a Word doc, and I can't import it into where I can write, but that's all right. We'll figure out how to get through. Where do you want to start?
I love these tests.
You love these tests?
Yeah, these ones are good. Yeah.
I had a question from Jeremy earlier today about the MA343 review type questions, and I'm not planning to put any of that on the final.
Yeah, there's
right?
like two of them like that.
Yeah, there's a couple of them. This number 2 is one of those.
And
Number 3 is one of those. But those are things you should just know. And so having that basic knowledge of what a confidence interval is and what a hypothesis test is will be essential to getting through some of the more complicated things, but I won't specifically test over it. All right, so
we go over number 10.
Number 10, okay. Let's see. You guys are telling me how to do this. There's 10. How about that? Okay, so number 10 says, recall the data on the number of tornadoes annually in the U.S., blah, blah, blah. The average of the year variable is 1979 with a standard deviation of 15.443. The average number of tornadoes was 895.5 with a standard deviation with a standard deviation of 284. The correlation equals 0.8 something something. All right, so what percent of variation in tornadoes can be explained by the year?
Year is a explanatory variable.
Okay, year is the explanatory variable, but I want to know what percent of the variability in the y variable, in the response variable, can be explained by that explanatory variable. What percent?
R squared.
That's R squared. And so, let's see, I need to do that. So this is R squared, which is 0.806 squared. Whatever that number is. Does everybody have
65%, or yes, 65.1% or something.
651, so 65.1%. Okay? To predict the number of tornadoes from the year, determine the equation of the least squares line. So you need the formulas that use the information given to get first the slope, and then once you have the slope, you can get the intercept. Right? So the slope is, that formula is R times SY over SX. Does this sound familiar? Okay. So R is 0.80629. SY is the standard deviation of the y variable, which average number of tornadoes was this, standard deviation 284. So 284.665 over 895. No. Let's put it in y bar. I want SX, which is 15.44. I guess it likes, okay. So then 15.443. So you guys need to be doing these on your calculator because I don't have the key handy to know what the answer is, but while you're doing it, maybe I can dig for the key.
14.8.
14.863. Okay? And that's the slope. Okay? Before I go on and get the intercept, let's go ahead and do part C, which says give the correct interpretation of the slope. What does that 14.86 represent? 14.86 what?
For every unit increase in year, there's 14.863 more tornadoes.
Increase.
I'm laughing because when you take a lot of math classes, I start to say, when you're a math major or a stats major, but you're not, but still, you've had a lot, you say things in a very precise way like that. For every 1 unit increase in the variable, so for each year, right? So each year, there's 14.86 more tornadoes than the previous year. That's what that number means. They're going up about 15 a year. And that's actually real data. This is just a fun fact, I guess. It doesn't have anything to do with what we're doing, but you know Jeremy Goodwin? You know who that is? Jeremy Goodwin? He's the chief meteorologist at Channel 13. Well, his wife took a class from me years ago, maybe 5 years ago, not that long ago, but so he was up here a few times with her when she'd come to pick up a test or whatever. And he heard me explaining this very thing in my office to a student about number of tornadoes increasing per year. And he came in, he said, wait. He goes, that's true, they are going up per year, but there's the old association does not imply causation, right? So the implication here is that it's global warming, right? It's climate change, which is true. It is causing the number of tornadoes, the number of hurricanes, and all that to go up. But he said there's also another factor going on. Can you think of what that factor would be?
People are just reporting.
That's exactly right. It's reporting bias. It's like back in the 1950s or whenever they started this, 53, then you didn't have all these people trained to be storm spotters and with zoom lenses on their cameras. So a lot of tornadoes were never noticed, right? They happen out in the middle of a rural area.
And there's more of us now.
Right, and there's a lot more of us to look at. He said, one thing that really struck me that I thought was interesting but funny, also, he said, and if you look at where tornadoes are reported, tornadoes really seem to hit a lot near interstate highways and near towns, right? So when you look at where they're reported, they're where people are, right? So, but now we have radar and all that can detect a tornado. So anyway, that's beside the point. But so what is B sub 0?
Intercept.
That's the intercept. And what's the formula to compute it? Remember our old friend, the point slope form of the equation of a line?
Y minus y1 equals mx.
Right. So if you know a point the line goes through and you know its slope, which we now do, then you can solve for the intercept. So the point it goes through is
1979 and 895.
right, exactly. X bar, Y bar. So 1979 and 895. So it's Y bar minus the slope times X bar. When you solve the point slope form for the intercept term, that's what you would get. So then we just plug in numbers. 1979 minus 14.863 times X bar, which is 895. Wait, I got them backwards, don't I? This is X bar, but X bar is not 895. Y bar is not 1970. Yeah. I got them flipped. So my old friend the eraser, that should be 895. So 895 goes over here. 0.509. Kind of getting crowded. And then this is 1979. Okay? So somebody should already have that clicked out. What do you get?
Negative 28,517.
Negative 28,517.
0.501.
I'll just say 0.5. when you're at 28,000 tornadoes, having another half of one, that's close enough, right? Now, what do you think about that as a interpretation?
It doesn't make sense.
Yeah, you can't have a negative number of tornadoes. Remember what the intercept is. It's the number of tornadoes predicted when X is 0. Well, first of all, X is year. So when is X 0?
On Jesus' birthday.
On Jesus' birthday, right? And so back then, we would predict there was negative 28,000 tornadoes. Well, it doesn't make sense to extrapolate the line that far. It's probably not a linear relationship over that time. It probably has become much steeper. So now you fit a line to this part. I should be doing it this way. It goes like this. You fit a line to this part, and it's going to extend way down instead of flattening out. But that's what it is. So the equation of the line then is y hat equal, and I'm just going to write the symbols, not write all the letters, but B0 plus that B1 times X, which is year. So you would just fill in these numbers. B0 goes there, B1 goes there. Okay? We already did part C. Part D says the mean squared error for this analysis is 28,911. Compute the predicted number of tornadoes for the future observation of 2006. Then give the standard error of the prediction and use the standard error to compute a 95% confidence interval. Okay, how in the heck am I going to do that? Predicted number of tornadoes for the year 2006. That's easy enough to do. So y hat, what do I got to do with the 2006? Plug it in here for X, right? So, again, I'm going to want to write all the letters out. B0 plus B1 times 2006. Right, so just substitute in what those numbers are. Plug it in, what do you get?
1297.
1297?
Yeah, 0.677.
0.677, so 0.7. If I go to one place. Again, to one decimal place for number of tornadoes is plenty accurate. Okay, so now give the standard error of this prediction. That's part of it. You said take the square root of the MSE, but the formula has more. Yeah, the formula is kind of nasty actually, but the standard error of y hat, what you gave me, root mean squared error is the standard error of the regression, right? But the standard error of a predicted value, remember there's two of those. You can predict the mean of all observations with that value of X, or you can predict a single observation with that value of X. Now, here it doesn't really make sense to say predict the mean of all observations with 2006, because how many 2006s are there going to be? Just one. But you get the idea. So, do you remember the formula? Okay, it has root MSE, then what's after that?
Square root of 1 plus 1 over n plus
X star minus
Okay.
the first year thingy.
So it's S sub E, which is, that's the root mean squared error. So I'll write that down here. Root mean squared error is SE. And then times the square root of 1 plus 1 over n plus, and now you need a term. You need a term for how far away from the centroid are you trying to predict, right? So remember I always do this with my fingers. If I have a line that's sloping up like this and it goes through X bar, Y bar, if I have error in my slope, then that tilts the line. So the amount of error in my predicted value is more extreme out at the ends. It's like being at the end of a teeter-totter, right? If you're near the middle, then it doesn't hardly affect it. So that's what this term is doing. It's saying, well, how far away from x bar are you trying to make this prediction? So it's x, and the formula we used has x sub 0, just meaning the value you're interested in. So for us, that's 2006. Then minus x bar quantity squared. Right? Then divided by, what's it divided by? N minus 1 times, okay, standard deviation squared, which is the variance, right? So if you think about it, I remember doing this at the time, but the book uses a couple of different notations. But for this thing on the bottom, if you take the variance of a variable and multiply by its degrees of freedom, what do you get? Let me go over to the board and use a marker. This is scratch paper. But if I have, if I want the formula for the variance of x, right? What is that formula? It's something divided by n minus 1. And what goes in the top? You learned this in MA343. Well, without the squared, I'd have a square root over this for the formula of standard deviation. So what goes on the top of this fraction? I'm giving a comprehensive final over a class that has MA340 as a prereq, and this is chapter 2 of MA340.
It was so long ago.
Yeah, it was a long time ago, but it's the sum of the squared deviations.
Yeah, that.
Right?
Oh, yeah, that.
So the sum of the squared deviations from the mean. Right? That's standard deviation. Right? So you're averaging the deviations. But you square them because you got to get rid of negatives. Right? So if I now multiply through by the bottom of this fraction, then I get what's on the bottom of that formula. Right? So if I put n minus 1 right there, then you could write this under that fraction instead of this. Right? So it's the sum of the squared deviations. Right? So it's the squared deviation of the point you're interested in as a fraction of the total sum of squared deviations. That's what this is. Right? Okay, so now we've got the formula. We just got to start plugging in numbers. So that's kind of nasty, but the square root of, they give us the mean squared error, 28,911.706. That's the first part. And then we have the square root of 1 over 1, or 1 plus 1 over, how many tornadoes did we have in this sample? 53. Or not how many tornadoes, how many years. Okay. So how many data points. And then plus, on the top is 2006 minus 1979 quantity squared divided by n minus 1 would be 52, and standard deviation of x squared. So they told us up here the standard deviation of x was 15.443. And then you're going to square that to make it a variance. So that's pretty ugly. But I was looking to see if I had the key that I would have the answers and I wouldn't have to wait on you guys, but apparently I do not. Oh, this is exam 1. I'm looking at the wrong one, no wonder. What'd you say, Leanna?
If we have it right, we don't really
Yeah, good. So did you get it right?
Yep.
All right, so tell me what the number was.
176.513.
176.503. 513. And my 5 turned into a 6. Point. Now you got to read me the decimals.
513.
513. Okay? So that's the standard error. So we're predicting about 1,300 tornadoes, but the standard error of that prediction is about 176. So I could be off 176 too much or 176 too little pretty easily. All right? So then use that to compute a 95% prediction interval. So what do you do with that? Multiply by what? By a t-critical value. Right? So scroll. Well, I don't have much room, but so you're going to use the point estimate, 1297.7 plus minus a t-critical value, which I'm going to leave as blank for now, times 176.513. And then how do you get a t-critical value?
Inverse T.
Inverse t function, if you happen to have the calculator that'll do that. Brent, yours does not. That's TI-83. But you can look at a t table. So the degrees of freedom for that t, n minus 2. Right? Remember, for a regression, the degrees of freedom are n minus 2. So we've got 53 observations, so we need 51 degrees of freedom, and we need 95% confidence. So look it up in a t-table. A t-table probably won't have 51 degrees of freedom. It'll probably have 50, then 60. It starts to jump after about 30. So you would use the closest one that is less. So you'd go to 50. But if you have inverse t, what do you get? What's the more exact value?
2.007.
2.007. Okay, so just give me the final interval.
943.478. And
I'm just going to say 0.5, just because I'm going to run out of room. And again, tenth of a tornado is fine.
and then 1,651.9.
Okay, that's a pretty wide interval, isn't it? How many tornadoes are we going to have this year? Well, I don't know, but probably between 943 and 1,600, somewhere in there. So that's almost, or that's, you know, what's half of 1,600? 800. So, you know, that's a pretty wide range. But part of why it's so wide, a couple of reasons why it's so wide. What's one of the reasons? What affects the width of the confidence interval? Sample size has a lot to do with it. So 53 observations isn't that many, so it's going to lead to wider prediction intervals. But then this standard error of residuals affects it also. So we've got a lot of spread here. We're only explaining what percent of the variability. I've scrolled it up there, but what did we say? 65%. So we got 35% of the variability still unexplained. So that's a fairly big standard error.
So for the big formula you wrote, where the 1 plus 1 over n, isn't there a formula that doesn't have the 1 plus?
There is. That's very good. So that part right there is for predicting an individual observation. If you predict the mean of all observations with that value of x, then that term 1 plus wouldn't be in there. Right. So I like to say that, you know, this formula has the pieces in it. You build this formula based on what are you trying to predict. If you're trying to predict a mean, like where's the line going to go above x, then it has a 1 over n, because remember from MA343 that the central limit theorem tells us that the standard error of a mean is standard deviation over the square root of n. Right? Well, here's your square root, 1 over n, there's your standard deviation. Right? So predicting where the mean goes, you need that term, plus a term that says, well, how far away from the x are you for the teeter-totter effect. Right? Well, now I want to predict an individual around that mean. So first I have to allow for error in where I got my mean. Now I've got standard deviation around that mean for every individual. So then you add another one of these SEs to get that.
So how do you know which formula to use? Like how would we know to use the other formula?
Okay, I'm going to give you a smart aleck answer. He asked, how do you know which formula to use? You look at your cheat sheet. That's the smart aleck answer.
Okay.
If you're predicting for an individual observation, the 1 is in there.
Okay.
If you're predicting for the mean of all values, all observations with that value of x, then the 1 is not there. So it'll say in here. So here's how it says: compute the predicted number of tornadoes for the future observation of 2006. Right. If I wanted you to not have the 1 in there, then I would have said, well, two things. I would have said, it doesn't really apply here too much, which is why I used this one, but predict the mean number of tornadoes predicted for all observations with an x of 2006. Okay. Plus, I wouldn't have called it a prediction interval. What do you call it? A confidence interval. So if they ask for a confidence interval around prediction, then the 1's not in there. If they ask for a prediction interval, then the 1 is in there. Okay? Next question. And by the way, we're down to 20 minutes left, and we haven't gone to exam 2 yet. So
Can we go to the variance on the last page?
of the second?
Yeah.
Okay. So if I go to the one I have as a PDF is the key. The other, without my work on it, it's going to be the I'm going to do that. And I want to make that bigger.
You just scroll with your hand.
Huh?
You just scroll with your hand, can't you?
I don't know. I tried.
Oh, yeah, you have to change it.
So I got to change the page, and then I got to make it bigger. So you want to go to the last page? That one? And you want this down here? It looks like this, when I did the key, I had extra questions in there. So maybe we should do the other one. But I think I can make this work. So let's make that bigger. And then is this the right one? This is not analysis of covariance.
It was the boxes and cells and something.
Okay, well, I'll tell you what. Let me let's see, I've got to go there. So this one, this is the Word document, and it's easier to manipulate. This one?
Yep.
Okay. So, marketing research was conducted to choose between 3 types of promotions. Cases is the number of cases of crackers sold during the promotion period. Type is the type of promotion. So there's 3 types. And then the covariate last is the number of cases of crackers sold in the preceding period. So below are unadjusted means for cases, for the variable cases and the variable last, both overall, averaging across the type, and then split out by type. Right? So part A says, how would you test whether the equal slopes assumption required for the validity of the ANCOVA model is met? How do you test whether the slopes are equal across the three types of promotions.
So then with the standard deviation, then place
The interaction.
yeah.
You fit the model with an interaction term between type and your covariant, which is last, right? So, in other words, does the slope or the coefficient of the variable last, does it change across the three types? And the way you check for that change is by an interaction term. So, if you look at output, did I not put it on here? Oh, I didn't have you actually do it. I just said explain how you would do it. So that's how you would do it. You would include an interaction term in the model, check to see if it's statistically significant. If it is significant, which conclusion is that?
You don't need the encoder model that way.
If there is an interaction, the slopes are the same or different?
The same.
No, they're not the same.
If there's interaction, the slopes are not the same, and COVID doesn't really apply.
Because one with the iron that went way up and the other went
Right.
down, or everything else was parallel.
Right? Okay, so then part B says, after adjusting for the number of cases sold in the last period, are there significant differences between the promotion types? So now you need to look at the SAS output. So after adjusting for the number of cases sold last time, are there differences in the types of promotion? Which line do I look at to test that?
Intercept.
You want the estimates.
I want to answer the question, is there a difference between the types after controlling for last? I just noticed it, but if you didn't have to point at which line or circle which p-value, you could answer that question without even knowing which one you're supposed to look at, because they're all the same.
Yeah.
Every p-value in here is less than 0.0001. Every p-value except the one on the intercept term. And that's not the one. And so it is going to be significant, but which one is the one you need to look at? This one right here. Let's see. That p-value, so this test for type after controlling for last, that's what that's testing.
What's the difference between the one above that one?
I don't talk about that much in this class, so I kind of breezed over it at the time, but these are called sequential, right? So type 1 sums of squares. These are type 1 are called sequential, and they're tested in the order they go into the model. Now here it doesn't make any difference for the type variable because it went in last, right? It's just the order they're listed. So after controlling for last, type. So notice that their sums of squares are identical. P-value, everything's the same. But look how last changes. Last here has a sum of squares of 190. Down here it's 269. So this one is, after you adjust for type, what is there left for the variable last to explain? So that number actually went up. It's kind of surprising, but by itself it's only 190. But after you adjust for type, then it goes up to 269. Okay, so this is the line that answers that question. Okay, so are there significant differences? And all I have there is a yes/no question, so you could just say yes. But I'll be more careful on the final. Say, indicate on the output which line it is that's testing this. Okay, now the hard part I think of this problem was compute the adjusted mean value of cases for type equal 2. Okay, so adjusted means. How do you compute adjusted means? So it's type equal 2, so I'm going to label that as y bar sub 2. Right? So y bar sub 2, sometimes I write like adjusted, sometimes I put an asterisk, so I'll put an asterisk just, and then I made a dot accidentally. There we go. So the asterisk indicates adjusted mean, and it'll be a function of the unadjusted mean. Now, do you remember what that function is?
Y bar
That's
sub
white bar.
Y bar sub 2 minus B sub 1, I think.
Yes.
And then X bar sub 1 minus X bar.
Not x bar sub 1.
2.
X bar sub 2 minus x bar dot. And what does the dot mean?
The grand.
The grand mean. Right? So what is b sub 1? That's the slope of the regression line regressing the number of cases sold in this period regressed on the number of cases sold in the last period. So it's the coefficient of the variable last. Right? So it's adjusting for the covariate, the x's. Right? And so you need to go to the output to find that value. The rest of these numbers, there's 3 other numbers, they're all in this table. So y bar 2 is, y is my y variable is cases, so that's 36. Right? So that's y bar 2. X bar 2 is the mean of the variable last in that second group. And where is x bar grand mean? That's up here, right? So it's the last variable when you're averaged across all of the promotion types. So all we need is that B1, and I can't see it from here. I got to go down and get it. So in my output, oops,
B1 is 20.
my writing is all, but B1 is right here. Yeah, it's the parameter estimate. The parameter estimate for the variable last. So it's 0.8986 if we go to 4 places. So 0.8986. Memorize that number. Ooh, went right back into place. Now I got extra writing though. But so that number. Oh yeah, I didn't change mine. There. So that thing is 0.8986. And I'll write here coefficient of last in SAS. Everybody understand what I mean by that? Okay? Does anybody have it computed?
You can do it in your head.
Yeah, I can, but I don't like to show off.
Like the whole, it's 36.8986.
36.896?
86.
8986?
Yeah. If you're taking it minus negative 8986.
Yeah, but I got to multiply that by here, right?
Just 1.
Is it 1?
It's negative 1.
Ah. So x bar 2, no, it should be 26.4 minus 25. So it's It's 1.4. Right?
It says 26.4.
Right? This is 26.4. This one is 25. So that would be 1.4, then times 0.896.
I have 34.
Did I mark this wrong on your test? Oh,
No, I was just going on.
you're okay.
Yeah.
I was going to come back and take some more points away. So that's not quite right. It's going to be close to that.
I have 34.754.
Okay. 34 point, say it again.
754.
754. Okay. All right, next question. Is everybody done with all this? And I'll hit the clear button.
Can we do number 9 on that test?
Number 9, okay. That was 11, so... Number 9. So we have a manufacturer of infant formula running an experiment on formulas A and B. The goal is to boost the immune system. So we have a sample size of 120 infants randomly assigned to one of 3 groups. Group A, Group B, or control. There are 40 infants per group, and the study is run for 12 weeks. At the end of the study, the variable measured is total IgA, which is Ig is kind of a prefix for immunoglobulin, right? Immunoglobulin A. So it's a marker of your immune system. So higher values are good. We run a one-way ANOVA, and it's given below. So let's creep up here a little. And one of the primary questions was whether formula B was significantly different than the control group. So we want to know, is B different from control? Provide the expression for the population contrast phi that, or that's not phi, that's psi. Again, my Greek letters. So the Greek letter psi that would be used to answer this question using μ's. So psi is equal to
Psi C minus psi.
Well, you're using
Mu control.
right. What?
Minus mu.
So I need the mu of the control group. So I'm going to put C rather than a 7. Usually we use 1s, 2s, and 3s or whatever, but just to keep it obvious what we're doing. The mean of the control group, I need the mean of the A group, and I need the mean of the B group. Right? And I just listed them in the order here. So C for control, A, and B. And now I need the coefficients of those that answer this question. So if I want expression for that would be used to answer this question, was B significantly different from the control group?
So control is 1 and B is 1.
Okay, so positive 1 for B.
No, it's a negative 1 for B.
Ah.
You
Does
could
it
make.
matter?
You could make.
It doesn't matter. You can make this one positive 1, but then this one should be
Has to be negative.
negative 1. And that would take B minus C. If you do it positive 1, negative 1, then you got C minus B. It doesn't really matter.
For the sake of different.
Right. So, since I already wrote a plus sign, I'll put the negative 1 over there. Now, what about the A group?
0.
That's a 0. So, plus 0, and you probably wouldn't actually write it in there. Then give the null and alternative hypotheses for a test of that contrast. Okay, well, what would the null hypothesis be? The contrast psi is equal to 0. And 0 would say there's no difference between those means. versus not equal 0. Okay. Then provide the standard error of the contrast in A. So what's the standard error of a contrast?
C over standard error or the con.
Not quite.
Standard error.
When you do inference in regression setting or a ANOVA setting, it always has it starts with pretty much the same thing, the root MSE, right? And that's your estimate of the variability in residuals or unexplained variability. So the standard error of the contrast C, and remember C is our sample estimate of psi, right? C psi. So that's going to be root mean squared error, or sometimes I write it as S sub E, and then times, what's the other part? The one we were just doing a while ago had the 1 plus 1 over n. It's the same
the square root of the sum of A3i squared over ni.
Now I wrote sum from little I equal 1 to capital I. And what's capital I?
The I groups.
It's the number of groups. And we've got 3 groups. So this will be a 3. And the AI is, what does that stand for?
Variance or the contrast times the variance.
These are the contrast coefficients. So A sub I, that's -1 is A sub 1, 0 is A sub 2, and +1 is A sub 3. All right, so A1, A2, A3. Okay? Now that's divided by
The ni.
in I. So how many you have in that group. Okay? So, what'd you say?
That would just be 40.
It would be 40 each time because there's 40 in each of these groups, right? So when they're equal, you could factor it out, but to make this general for possibly unequal sample sizes, you leave it general, right? So then it's just plugging in numbers. You've got the MSE right here, right? Error, and then I've scrolled up, but top of this says MS for mean square. So the mean squared error is 00252. That'll go under here. Take the square root of that. And then the AIs 1, 2, and 3, each of them squared, which is just getting rid of the negatives, over 40. So you're going to get 1 over 40 plus 1 over 40, which is 2 over 40. So this will default, I can actually do it in my head, to 1 over 20, right? So square root of 1 over 20, I can't do that in my head. Multiply by the square root of that root mean squared error, and you have the standard error. The next part, I'm out of time, but the next part probably asks for a confidence interval. Oh, do a test statistic. So then if you were going to do a test, you take the estimate of the contrast C, which we haven't done yet. It's probably coming up, right? You would estimate the contrast by just taking the difference in these means. So we have -1 times the control mean and +1 times the B mean. Add those together. And then divide it by the standard error, and you got a T test statistic. So the value of the contrast divided by its standard error. Right, so the test statistic T is C over standard error of C. Technically, it's C minus the hypothesized value psi 0, but that's almost always a 0 from the null hypothesis. So this is your psi sub 0, right? So then it just drops out. And then you need to know degrees of freedom for the T to decide if it's significant and all that. So what would your degrees of freedom be? 117.
Freedom error.
When in doubt on degrees of freedom in a regression or in an ANOVA setting for a t-test of any kind, it's the error degrees of freedom from the ANOVA part of the model. All right. That's all I know about that. So good luck studying. We will see you Wednesday, 9 a.m.?
1:30.
1:30. Wednesday at 1:30. And let me know between now and then if you have questions.